Today we are going to see yet another use of derivatives to measure sensitivity to change. Say you have a function f of x, and for a small change in the x value, the function value changes significantly. The change in the function value is large. Then we say that f is relatively sensitive to change in x, and the derivative of f at x can be considered as a measure of the sensitivity to change of the function at x. That is, it measures how sensitive f is to change in the input value at x. Now, to illustrate this, let's look at this example. In this example, we have the famous Austrian monk Gregor Johann Mendel. You already probably know about him from genetics. So he was the first who gave a scientific explanation of the process of hybridization, where interbreeding between different species happens and the offsprings are hybrids. So they get characteristics of their parents. So from Mendel's research and his records, this is what he found. So he was researching on two different types of garden peas. In one of them, the peas have smooth skin, and in the other, they have wrinkled skin. And specific genes are available for these skin types. So if P is the frequency of the gene responsible for smooth skin in peas, which is a dominant characteristic, a dominant trait. P is a number between 0 and 1, I forgot to write that. And 1 minus P is the frequency of the gene for wrinkled skin in peas. Then the proportion of the smooth skin peas in the population at large is this, which is Y. And that is 2P times 1 minus P plus P square, or 2P minus P square. So this means that the proportion of smooth skinned peas in the population, if P is the frequency of that gene responsible for smooth skin in peas, is this. Now if you draw the graph of this function with P along the x-axis and Y along the y-axis, then you get this graph. So from the graph you can see that when P is very close to 0, the change is more. So Y is more sensitive to change in P when P is small, and less sensitive to change in P when P is large. When P is close to 1, the change is not really that much, and the sensitivity is measured by this derivative dy dp, which itself goes down because it's 2 minus 2P. So you can see here also, when P is close to 0, the sensitivity is quite high. So around that P which is close to 0, if P changes a little, then Y changes a lot, which is what we see here. Whereas when P is very close to 1, then the sensitivity is quite low. In this region, Y does not really increase that much. Now we are going to see more about this use of derivative as a measure of sensitivity in another section, which will come in the 3rd chapter. After this, actually there is one more application where we see the use of derivative in economics, where we use derivatives to measure marginal cost and marginal revenue. However, let's do that another day, because that has some, I think 2 or 3 examples after the main concept, and that will take some time. If I include that in this video, it will become very long. Okay, so that's just it for tonight. It's extremely short, I know, but it is what it is. And tomorrow, of course, we again have our usual linear algebra. So that's just it for tonight. So see you tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.